Richard James Mathematics Resources will now present grade 4 practice paper for part B. And as we said before, A, B, and C all contain the solution of 12 problems. So this part B is therefore the solution of another 12 problems. And we will begin at number 13 and end at number 24. Which of these would be the least common multiple needed to add the fractions 2/5 and 1/3? So we need the least common multiple required to add the fractions, which are 2/5 and 1/3. When adding fractions, we need the least common multiple of the denominators. So I am asking Jerry, if we need the least common multiple of the denominators, what are the two numbers that we need the least common multiple of?
5 and 3.
Right, 5 and 3 are the denominators. Therefore, we need the least common multiple of those numbers, the denominators. So we are magnifying those fractions that we may have a closer look at them. Not only that, if we say denominator, which one of those numbers do we mean? So we have labeled the numerator, the denominator, and the fraction bar of those two fractions. So we need the least common multiple of the denominators, and those will be 5 and 3. So those are the two numbers that we need the least common multiple of. So those are what we need the least common multiple of: 5 and 3. We will first take a look at the multiples and later on deal with least common. So we'll start off with the multiples and then say what least common means. A multiple of a number is the product of that number and a natural number. So a multiple is the product of the particular number and another natural number. We need multiples of 5 and 3. We need to multiply 3 and 5 by natural numbers. Write down some natural numbers. The fancy N is the symbol for the set of natural numbers. So the natural numbers or counting numbers are numbers like 1, 2, 3, 4, 5, 6, 105, 7,256. Those are all natural numbers. For multiples of 5, multiply those natural numbers by 5. And for multiples of 3, multiply those natural numbers by 3. So what are the multiples of 5 that we will have here, Jerry?
1.
What are the multiples of 5 that we will have there? We will have the multiples of 5 here because we are multiplying these numbers by 5. So we'll have what?
5, 10, 15, 20, 25, 30, 35.
All right, Jerry. We'll not go that far. So we'll have those are 5, 10, 15, 20, 25, and 30. Right. And for multiples of 3, let's put the natural numbers down. Those are the natural numbers. And for the multiples of 3, what will the multiples of 3 be?
3, 6, 9, 12, 15, and 18.
Right. So those will be the multiples of 3. We could go on and on and on and more ons, but this list contains the LCM of 5 and 3. So we may stop here. Now, I'm just illustrating what least common multiple means. The lists that we have here are enough to give us the least common multiple or the lowest common multiple of 3 and 5. So we will not go any further. We need the least common multiple. Common means that it is present in all. The multiple that we seek must be in the list of multiples of 5 and in the list of multiples of 3. So the common multiple that we need, common means it is present in all. So it is present in the list of multiples of 5 and in the list of multiples of 3. So look in the two lists, Jerry, the two lists that we have there. We have the list of multiples of 5 right here, the list of multiples of 3 right here. Which number is present in both lists?
15.
15 is present in both lists. That means 15 is a common multiple of 3 and 5. But is 15 the least or the lowest common multiple of 3 and 5?
Yes.
Yes, it is. It is because there is no other number that is in the list of multiples of 5 and 3 that is smaller than 15. So 15 is the smallest, the lowest, or the least common multiple of 5 and 3. So those are the multiples of 5 and 3. Find all the numbers that are in both lists. And I asked Jerry already, and Jerry told me that the number that is present in both lists is
15.
15. So there we have that 15. 15 is in both lists. It is a common multiple because there is no common multiple (15) is in both lists. It is a common multiple because there is no common multiple that is in both lists that is less than 15, then 15 is the least common multiple. So in both lists that we have there is no multiple that is less than 15, or no member that is in both lists that is less than 15, then we are sure that 15 is the least common multiple. The correct answer is therefore
Option D.
Option D. Let us take a look at more multiples of 5 and 3 than what we had on the previous slide. So we had multiples of 5 and 3 on the previous slide. Now we will take a look at multiples of 5 and 3, more multiples of 5 and 3 than we had on the previous slide. So those are our multiples of 5, a greater number of them, and those are our multiples of 3. So we have longer lists than we had on the previous slide. Let us identify the common multiples of 5 and 3. I'm going to ask Jerry again. What are the common multiples of 5 and 3, Jerry?
15.
Do we have any other in the lists?
No.
Jerry is saying no because
Yes.
Jerry did not look. All right, so
30.
right, he's saying that yes, there's another one which is
30.
right. So there's another one which is 30. There they are. In the list, we have two common multiples of 5 and 3, 15 and 30. The smallest common multiple that we can find in the list is
15.
Since there is no common multiple of 3 and 5 that is smaller than 15, it means that 15 is the least common multiple of 5 and 3. Let us take a second look at the least common multiple by using a table. So let us use a table. Although we do not need it, it is clear from the table that there is no number apart from 1 that can go into both 5 and 3 without leaving a remainder. In any case like this, the LCM of the numbers will be the product of the numbers. So let us mention that. Notice that there is no number apart from 1 that can divide into both 5 and 3 without leaving a remainder. It means that 5 and 3 do not have any common prime factor. Because 5 and 3 do not have any common prime factor, it means that the least common multiple of 5 and 3 will be the product of those two numbers. So for example, if we are taking a look at 4 and 9, what is the LCM of 4 and 9? Because 4 and 9 do not have any common prime factor, then the LCM of 4 and 9 will be 4 times 9, which is equal to 36. So that is a rule that students may apply when working with lowest common multiple. If the two numbers do not have any common prime factor, then the LCM is the product of the two numbers. What about 4 and 6? 6 divided by 2 is equal to 3. And 4 divided by 2 is equal to 2. So, do those numbers have any common prime factor, Jerry?
Yes.
And what is that common prime factor?
2.
Right. So, because 6 and 4 have a common prime factor of 2, it means that the LCM of 6 and 4 is not 6 4s 24. So, since 2 can divide into both of them without a remainder, it means that the LCM of 4 and 6 is not 4 times 6, which is equal to 24. Consider 9 and 8. Do they have any common prime factor, Jerry?
No.
Because they do not have any common prime factor, then the LCM of 9 and 8 will be 9 times 8. The only number that divides into both 8 and 9 without a remainder is 1. The LCM of 8 and 9 is therefore 8 9s 72. There is another rule of thumb that we may consider. What is the LCM of 4 and 12? Some may quickly say 24, and others may go ahead and multiply 4 by 12, which is equal to 48. They will do this without giving consideration that 12 is a multiple of 4. Because 12 is a multiple of 4, it means that 12 is divisible by 4. And also, every number is a multiple of itself. The LCM of 4 and 12 is therefore 12. So, 4 can go into 12 without a remainder. It means therefore that 12 is a multiple of 4. So, 12 is a multiple of 4, and every number is a multiple of itself. It means that 12 is a multiple of 12. So, 12 is a multiple of 4. 12 is a multiple of 12. Therefore, 12 is a common multiple of 4 and 12. Not only that, but 12 will turn out to be the LCM of 4 and 12. If one number is a multiple of the other, then the LCM of the numbers is the larger number. So here we go, Jerry. Say 18 and 6. What is the LCM of 18 and 6? Right, because 6 can go into 18 without a remainder. It means that 18 is a multiple of 6. And 18 is a multiple of itself. So what is the LCM, Jerry, of, say, 28 and 7? What is the LCM of 28 and 7, Jerry?
28.
28, because 28 is a multiple of 7. And every number is a multiple of itself. So 28 is a common multiple of 28 and 7. And it is the smallest such number. So 28 is the LCM of 7 and 28. The LCM of 3 and 15 is 15. The LCM of 4 and 8 is 8. The LCM of 8 and 24 is 24. The LCM of 10 and 50 is 50, and so on. 10 sweets were shared among 4 children. Demi got 1/10 of the sweets. Angie got 3/10 of the sweet. Gavin got 5/10 of the sweets. And Kwesi got 1/10 of the sweets. Who got the most sweets? That is the question. And Jerry is already outlining that Gavin got the most sweets, because all of the denominators are equal to what, Jerry?
10.
Right. So all of those are out of 10. Therefore, the one that got the largest or the greater number out of 10 will be the one who got the most sweets. And Jerry said that Gavin got the most sweets. However, let us look at the finer details and some of the principles that we may consider in solving a problem like this. Well, we have solved the problem already, but our mathematical principles will not be just limited to this particular problem, but for other problems and throughout our entire life in mathematics. The problem is given with fractions with 10 as their denominator. Before going into the sweets, we will take a look at the significance of fractions with 10 as their denominator. The fraction that we have there is 1/10. A tenth is one of the 10 equal parts of a whole. It therefore means that the whole is divided into 10 equal parts. So we say that the fraction that we have here is 1/10. 1/10. 1/10 is one of the 10 equal parts of a whole. And we have our fractions well prepared for us with its labels. The denominator tells us the number of equal parts that the whole is divided into. The whole is divided into 10
equal parts.
10 equal parts. The numerator tells us the number of those equal parts that we are talking about. And the numerator is equal to what in this particular case, Jerry?
1.
Right, so we have one part out of those 10 equal parts of a whole. Since we are dealing in tenths, let us divide a shape into 10 equal parts. And there we have, Jerry, a 10-sided figure. What is it called, Jerry?
Decagon.
Right. So we have a decagon. Jerry is very sharp. We have a 10-sided figure. And Jerry is not limiting his knowledge or his recollection to the problem that we are solving right now. As a matter of fact, Jerry is well prepared to tell us what a 10-sided figure is called. And it is called a?
Decagon.
Right, it's called a decagon. Right. So we have our decagon divided into 10 equal parts. On the next slide, we will treat the problem as a shape that is divided into 10 equal parts and give each child his fraction of the entire shape. After that, we will go to our 10 sweets and give each child his share. So we are taking the approach of using a single figure that is divided into 10 equal parts because that is what is suggested by the denominator of the fractions. But the problem has to do with 10 sweets that were shared, and we will see how that relates to a whole that is divided into 10 equal parts. Demi got 1/10. 1 part out of 10 parts. That is what 1/10 means. 1 part out of 10 equal parts. So Demi, you take your 1 part. What about the other one? Angie got
3 parts.
3 parts. So 3 parts out of 10 parts. Or 3 parts out of 10 equal parts. Angie, you need your 3 parts. There we have 3 of them. Those are your 3 parts out of 10 equal parts. And Gavin got 5/10. So 5 out of 10 parts. So Gavin will get how many parts out of 10?
5.
5 equal parts. How many parts are left?
1.
Well, Demi will get that one. No? Who will get that one? Yes, Quasi will get that one. So 1/10 is what is left. So only 1 part that is left. So each child received his sweets, or his or her sweets. Which one got the most sweets, if we can count the number of? Gavin. Who got the most sweets? It is clear who got the most sweets, although we do not have the sweets on the slide just yet. What we have there is because of the denominator of 10, we take a single object and divided it into 10 equal parts and share them because each equal part will represent one of those sweets. And we will see that on a subsequent slide. So Gavin got the most sweets. He got 5, and that is represented by option C. We will now make use of the 10 sweets. When we were in primary school, the girls used to sing a song. Lollipop, lollipop, teach me how to sing. Do you remember that?
Yes.
Okay, do they do it these days?
No.
Right. Right. So we have, how many sweets do we have there, Jerry?
10.
We have 10 of them. And those 10 sweets represent 10 parts. of a whole. The whole is divided into 10 equal parts that are 10 suites. Each suite will be one of the 10 equal parts. The numerator tells us the number of equal parts or the number of suites that each one gets. So who got the most suites? The one with the largest numerator gets the largest number and therefore the most suites. Gavin has the largest numerator and gets the most suites. He is at option C. Let us now do the actual sharing of the suites. Show who got the most. So there we have the fractions with their respective numerators. So 1 suite out of 10. Three suites out of 10. Gavin. Good. The one that is left will just remain for the other individual. Who got the most suites? Gavin got the most suites. And that is represented by option C, as we discussed earlier on. A mathematics club began with 82 members. During 1 year, 36 members left and 28 new members joined. How many members did the club have at the end of the year? And Jerry is attacking the problem already. A mathematics club began with 82 members. During 1 year, 36 members left and 28 new members joined. "36 members left." If 36 members left the club, Jerry, will that result in more or less?
Less.
What do we therefore do?
Subtract.
Okay, so the 36 members who left will reduce the number of members in the club. We will subtract 36 from 82, thereby getting our smaller number.
46.
Make up your mind, Jerry.
46.
We cannot take 6 from 2, so we go to the greater place value and rename 8. Right. So we have 8 tens there. And we take out 1 10 and 7 will remain. And that 1 10 we add to the 2 and we will get 12. So we say 12 minus 6 and that is equal to 6. Then we say 7 minus 3 and that is equal to
4.
And Jerry said that the result is actually 46. That's very nice, Jerry.
Add the 28.
And Jerry said that we should add the 28 to what? To 82? To 36?
46.
Okay, so add it to the 46. So 28 new members joined. So to the present number of members of the club, we will add the number of those members who joined. And the new members who joined will increase the present number of the club. increase the present number of club members, we need to add 28 to the present number. And Jerry is saying that that is 74. Jerry likes to do little arithmetics, you know. So as soon as he's required to add or subtract, even multiply, he's right on top of it in a flash. So Jerry has the answer already. So we add. So 6 plus 8 is equal to 14. Write 4 and carry 1 to the tens column. Let's go. And what do we get there?
7.
Right. So put that down. We get 74. So Jerry got 74, and he said that a long time ago, that the correct answer is 74, and that is represented by option B. The answer makes sense because more members left than those who joined. Right? The final number has to be less than 82. So remember now, we have how many leaving?
36.
And how many joining?
28.
Which is a larger number?
36.
Right, so the larger number left the club. Therefore, in the end, the number that we have must be less than 82. That makes sense. Is there any other way? Alright, let us take a look at this, Jerry, and see if you can figure it out. More mathematics. More left than those who joined. Those who joined will reduce the number of those who... Right. So, those who joined will reduce the number of those who the club lost. Overall, the club lost what? 36 minus 28 members, because 36 came out and 28 went back in. Therefore, effectively, those that are out will be what we get when we take 28 from 36.
8.
That's right, Jerry. Jerry's saying that is 8. So, more left than those who joined. Those who joined will reduce the number of those who the club lost, right? So overall, the club lost 36 minus 28 members. We cannot take 8 from 6, so we go to the greater place value and rename the 3. What will happen? 2 and the 1 that is removed from here will go into this column. And do not forget that if we are talking about this column, the column to the left, that place value is 10 times the present place value. Therefore, what we have coming from this is 10. And the 10 will be added to the 6. And that will give us what?
8. 16.
Right. It will give us 16. And we will take 8 from that 16, and Jerry said that it will give us
8.
And Jerry had the 8 in his mind all the time. So any answer that you ask for, Jerry will say that it is 8. Alright. So we will say 2 from 2, and the result is?
0.
Do we need to put the 0 here?
No.
If we put it there, would it be wrong?
No.
Right. But because a leading 0 or a 0 to the left of a whole number does not affect its value, then it is not significant that we should include it. So a mathematics club began with 82 members. Overall, the club lost 8 members. Those will reduce the number of members that the club had at the beginning. So we will subtract 8
From 82
from 82 gives
gives you 74.
74. That's what Jerry said. That we should take the 8 from the 82 and we will get 74. Right. We cannot subtract 8 from 12, so rename 8. And the 1 is 1, 10. So a 10 will be added to the 2 and we will get 12, from which we take that 8. So 12 minus 8 is equal to
4.
And with nothing to take away from the 7, it returns as it is. Right? So, nothing from 7 will give 7. And the answer is?
74.
And that is represented by option
B.
Right. So, what we could have done, that's another approach that we could have taken to the problem. We realized that more left the club than those who joined. So if we subtract those who joined from those who left, we will have the effective number of members who left. And that effective number of members who left, we can take it from the 82, which is the total number at the beginning. And we will get the number of club members at the end of the year.
So easily understood.
And Jerry is saying that is very simple. And I will say exactly what Jerry said. It is so easily understood. But what I want Jerry to do is to take a look at the actual club members, because we have the club members and we have the clubhouse. So we will take a look at that on the next slide. So we have there our mathematics club. Our mathematics club, and we have some writing on our club. One saying, mathematics make magnificent minds, and mathematics minus mental midgets. Right, so mathematics minus mental midgets, and we have mathematics makes magnificent minds. So we have our mathematics club, and what we will show 36 members leaving the club. So there we have our 36 members leaving the club. All of 36 members leaving the club. And Jerry is right on time to see the last of the 36 members leaving the club. So we have those running out of the club, going away. Those members leaving the club. So what we will do now is show 28 members joining. Remember that?
Yes.
Right. So we showed just now 36 members leaving. And how many of those members will join?
28.
Right. It does not matter if it is 28 of those who left, as long as it is 28. So it may be 28 different members, or it might be 28 of the same members returning to the club. The effect will be the same. It does not matter. So we have now 28 members running into the club. What will happen when those 28 members go back inside of the club? We'll take a look at what will happen. We had 36 running out of the club. Now we have out of that 28 running into the club. Because of the nature of the slide, we are using 28 of the same members. But it does not matter if it is 28 of the same members or 28 of other members, as long as we have 28 joining. The effect, overall effect, will be the same. See that, Jerry?
Yes.
Okay. Our question is, effectively, how many members left the club? So how many members are outside of the club now, Jerry?
8.
8. Maybe Jerry did not count them, or he counted them a long time ago. But because of the nature of the problem, and Jerry was very sharp with his arithmetic, he is just looking at it and say, well, it's the same 8 that we had before. But we will count them, and we will ensure that what we have is 8. The effect is as if only 8 members left, as we saw just now, which is what we calculated before. That is why we may only subtract 8 from 82, as we did in the second take of solving the problem. What is the value of the underlined digit in 16,574? What is the value of the underlined digit in 16,573? So what is the value of that digit, Jerry?
6,000.
Right, Jerry saying that is 6,000. That's right. Although some students may see the answer immediately like Jerry did just now, we may first write down the number that is given. That is the number that is given. We may next apply the place values. Place values are assigned from right to left. So we will begin at the right. And at the right, we will find what digit, Jerry? Which digit?
The 3.
The 3. And the 3 is of what place value, Jerry?
Ones.
Right, 3 ones. And then the tens, which will be 7 tens. And then after the tens, we have the?
Hundreds.
Right. And after the hundreds, we have the?
Thousands.
And after the thousands, we have the tens of thousands. But we are saying because we are at the underlined digit, we may say that the correct answer is option A, which is 6,000. Although the answer was determined already, let us include the tens of thousands place value. So there it is, tens of thousands. Knowing place values and the format of numbers, especially that a number is written in groups of 3 digits, some candidates may determine the answer immediately like Jerry did. So because the candidates are fully aware of the digits and their place values, and it is even important that numbers, that we understand that numbers are written in groups of 3 digits, that will also help. There are 30 cookies to be shared among 8 children, and Jerry wants all of the cookies for himself. Jerry is smiling, man, because he knows that it is true. Each child gets the same number of whole cookies. How many whole cookies did each child get, Jerry? How many whole cookies did each child get? We are saying that we have 8 of them, and that is 8 children, and we have 30 cookies. Right? 30 cookies. How many cookies did each child get?
38. 3.
Right. So Jerry is saying that each one got 3. Right. So 3 is correct. And that is represented by option
D.
right. However, we will put down our 30 cookies. How many cookies in all? 30 cookies. And I am not putting them down in groups of 8 because Jerry would trick me. So, so I put them down in groups of 10 so that Jerry does not overpower me that easily. But Jerry found the answer already, so that's okay. So, shared among 8 children. So let us say that we have the 8 children right there. 8 of them. Take the cookies in groups of 8 and give one to each child. So if we have 30 cookies to be shared among 8 children, we have the 8 children. One way to do it is take them 8 by 8 and give one to each child. That's correct?
Yes.
Okay. So take out 8 and give one to each child. Then what will we do again?
Take another 8. Take another 8.
Right, so Jerry said that we should take another 8. Right. Well, we will take 8 more. And what do we do again, Jerry?
Take another 8.
Okay, Jerry's saying take another 8. So let's go ahead. Take another 8. What do we do again, Jerry?
Can't take another 8.
I think that Jerry would say take another 8. But he's saying that we cannot take another 8. So how many cookies did each one get, Jerry?
8. 6. 3.
Okay, so each one got 3 cookies, as you said before. So there we have the leftovers. We do not have as many as 8 remaining. Each person cannot therefore get another cookie. So we have how many remaining? 6. We have 6 cookies remaining. Therefore, each person cannot get another cookie. How many whole cookies did each child get? So 3, right. Each one got 3 cookies. When there were enough cookies for each child, each one got 3 cookies. The correct answer is therefore option D. Right, so when there were enough cookies for each child, each one got 3 cookies. The 6 cookies that remain are naturally called the remainder. So the 6 cookies that remain will be the remainders. The word share implies division. The word share implies division. The cookies are shared among 8 children. So let us divide the number of them by 8. So how many cookies do we have?
30.
And we are dividing that for 8 children. So what do we say? We say 8 into 30. And do not forget that when we are dividing, we make use of our multiplication tables. Because if we know our multiplication tables, then that's easy for us. So let us take a look at our multiplication table, Jerry. What do we say for 8? 8 ones?
8.
8 twos?
16.
8 threes?
24.
8 fours?
32.
Right. So because 8 fours, 32, which is greater than 30, 8 cannot go into 30 4 times. So 8 will be able to go into 30 3 times. We will first attempt to divide 8 into 3. We can't. So we say 8 into 30 equals 3 times, right? And place the 3 above the 0. The correct answer is option D. Right. When dividing, give consideration to the multiplication table of the number that we are dividing by. We are dividing by 8. So we need to give consideration to our what timetable?
8 times.
We need to give consideration to our 8 times table. There it is. And Jerry knows his multiplication table. So he's not going to be flustered by the fact that we put those on the screen and then remove them very quickly. That will not affect Jerry the least bit. He knows the answer already. 30 is not a multiple of 8. So say it like this. The last greatest multiple of 8 that is less than 30 is 24. So the greatest multiple of 8 that is less than 30 is 24. 3 8s, 24. The whole number of times that 8 can go into 30 is therefore 3 times. Because if we say 4 8s, that will be 32, which is greater than 30. So we know that 8 into 30 is 3 times. Let us write 6 and 7/10 as a mixed number. The closed line measures 6 and 7/10 meters. Which of these shows the length of the closed line? 6 and 7/10 meters. That's the length of the closed line. 6 and 7/10 meters. Which one of those that we have in the option shows the length of the closed line? So let us write 6 and 7/10 as a mixed number. 6 and 7/10, or 6 and 7 over 10. Why are we highlighting the answers that we have in the option? Because all of those answers contain decimal fractions. The vulgar fraction must therefore be written in decimal form. Right? So it must be written in decimal form. Our fraction that we have there must be written in decimal form. So how do we do that? We need to divide 7 by 10. The 1 0 that follows the 1 in the number 10 tells us that we need to reduce by 1 place of decimal. So when we are dividing by powers of 10, like 10, 100, 1000, the number of zeros that we have here tells us the number of places of decimal that we need to reduce 7 by. Because we have 1 0, we need to reduce 7 by 1 place of decimal. We first need to locate the decimal point. In a whole number, the decimal point is located to the right. So we will reduce 7 by 1 place of decimal. The result will be smaller than 7. We may also place a 0 to the left of the point. So there we have 7. 7 is a whole number. In a whole number, the point is located to the right. We will reduce 7 by 1 place of decimal. And we do it like this. 1 place of decimal. And we also include that leading 0. It is not good manners to write an answer like 0.7, but to write it as 0.7, declaring explicitly that there is no whole number. The answers are not only in decimal form, but they have 2 places of decimal. Notice that the answers, these answers, have 2 places of decimal. So the answers have 2 places of decimal. A trailing 0 does not affect the value of a decimal fraction. So let us increase the number of decimal places to 2 places of decimal by including a trailing 0. So there's our trailing 0. The 6 that we have there represents 6 wholes. 6 that we have here represents 6 wholes. In a whole number, the decimal point is located to the right. The decimal points also need to be vertically aligned. So, in a whole number, the decimal point is located to the right. And the decimal points need to be vertically aligned. So we are going to combine the 6 that we have here with the 7/10 that we have there. Include trailing and placeholding zeros as their presence after the point does not affect the value of the number. So we may put in those trailing zeros because they do not affect the value of the number. The "and" that we have there means that 6 and 7/10 are in an addition relationship. That's what we are saying. 6 and 7/10. It means that the relationship between the 6 and the 7/10 is that they are added. So we will add them, and that we will do on the next slide. So let us be reminded of the place values of the numbers, or the place values of the digits. And Jerry likes to add these, although Jerry pretty much likes to add any number that you give him. But why do you enjoy adding these, Jerry?
Oh, they are single digits. They aren't zeros.
Right, because every number that we're adding there, we're adding 0 to that number. And when we add 0 to 7, the result is?
7.
And when we add 0 to 6, the answer is?
6.
Right. So we will begin our addition as usual with the rightmost digit. In this case, it is the 100th digit. And very quickly, 0 plus 0 is 0. Jerry likes that. And then moves to 7. 7 plus 0 is?
7.
7, and not 0 as some said. And then we will cause the points to be vertically aligned. And then finally, add the ones or units digits. Right, because of those zeros that Jerry needs to add. He is very happy because the addition process is very simple. There's no working of the brain and no working of the fingers. The correct answer is option B. After writing 6 and 7/10 as a mixed number, the number still has a whole number part and a fractional part. So we will write, as a matter of fact, we have written it already as a vulgar form. Write the fractional part as a decimal fraction by reducing 7 by 1 place of decimal, according to the single trailing 0 in 10. So when we are writing a decimal fraction, if we have a power of 10 in the denominator, the number of zeros will tell us the number of places of decimal by which we need to reduce the number. We have only 1 0, so we will reduce by only 1 place of decimal, and that we have done before. So there it is. The whole number part is 6. The whole number is always to the left of the decimal point. That's all there is to it. So what we have done is convert the vulgar fraction to decimal form, and we just include the 6 with it. And the 6 is the whole number. The 6 that we have here represents 6 wholes. And the whole number is always to the left of the decimal point. A trailing 0 to the right of the decimal fraction does not affect its value. So we place that trailing 0 right there because it does not affect the value of the decimal fraction. Option B is therefore correct. The problem may be greatly simplified by considering the place values of the digits that are implied in the problem. The problem may be greatly simplified by considering the place values of the digits that are implied in the problem. The 6 is going to be 6 whole, and its place value is going to be
1.
Right, and then we have 7 what?
10.
Right, that's all. We're going to have 6 1 and 7 tenths, and that's all there is to it. 6. The 6 that we have there is 6 ones. It is the whole number part and goes to the left of the decimal point. 6 ones. 7 tenths. 7 tenths. Notice the TH ending. Tenths. 7 tenths. The 10th digit is the first digit to the right of the decimal point. So the 7 will go right there as the first digit to the right of the decimal point. Include a trailing 0 after the decimal fraction in order to be in harmony with the formats of the options. Notice that we have 2 places of decimal there, so we may include the trailing 0 right there. And the trailing 0 after a decimal fraction does not affect its value. Option B is our correct answer. Right. So instead of going through all of that, we could have just used place values, and that would be shorter. However, throughout our entire life in mathematics, we need to make use of the principles that are discussed, and that is why I always make mention of other fundamental principles that may be used to solve a problem, instead of just giving the solution of the problem only. I am making use of something that all young mathematicians will find very useful in the long run. Janelle is the 10th person in a line of girls. What position is next behind her? So Janelle is the 10th person in a line of girls. What position is next behind her?
11th.
And Jerry is saying it is?
11th.
Right, is 11th is the one next behind her. If we have a line of girls, the one who is at the front is number 1 and is in what position, Jerry?
First.
Right, first. Next behind her is the person who is assigned number
2.
and that person is in what position, Jerry?
Second.
Right, and the one after second is?
3.
And that will be what position?
Third.
Right. And those numbers are called what kind of number, Jerry?
Ordinal.
Right. Those numbers are called ordinal numbers. So we have the first, the second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th. And right after 11th we have 12th. So first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. There we have Janelle going up. Is the 10th person. Next behind the one who is in the position next behind her is the one who is immediately behind her. The very next one. So we have the one that is immediately behind her. Janelle is 10th, which is position number 10. The one next behind her is the one that comes after, which is number 11, and is therefore in 11th position. The correct answer is option
D.
D, right there. Five cakes were cut into thirds. How many thirds were there in all? 5 cakes were cut into thirds. How many thirds were there in all? 5 cakes were cut into thirds. A third is 1 part out of
3.
just 3. 3.
Wholes. 3 equal parts.
Right. 1 part out of 3 equal parts. Do not forget, Jerry, when we are dealing with fractions, the number of parts that we are dividing into must all be
Equal.
right. So there we have numerator, fraction, bar, and denominator. We are focusing on this occasion on the denominator. And the denominator is?
3.
And that tells us that each one is divided into how many equal parts?
3.
Right. So the denominator tells us the number of equal parts that the whole is divided into. Let us divide each cake into 3 equal parts. So each one is divided into 3 equal parts. And we are making sure that we not only divide each one into 3 equal parts, but we are also numbering
15.
those 3 equal parts. And Jerry is saying that the answer is 15. Right. Let us find out the number of thirds in all by counting the total number of thirds in the 5 cakes. So how many thirds are in the 5 cakes? Jerry said that we had what?
15.
15. So let us see if we have 15. We count 3,
4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
that's it. 15. There are 15 thirds in all. The correct answer is option
A.
5 cakes were cut into thirds. The same problem. What do we make of it? There are 5 cakes cut into thirds. The cakes are cut into thirds. We need to know how many thirds. We may say that the 5 cakes are divided into thirds, and as such proceed to divide 5 by a third, or 5 by 1/3. So the cakes are cut into thirds, and we need to know how many thirds we have there. Therefore, we need to divide whatever number of cakes we have by 1/3. On the other hand, we are really attempting to determine the number of thirds that are in 5. How many 5s are in 20, Jerry?
4.
How did you arrive at that answer?
By divided.
We will do the same right here. How many thirds are in 5? We will divide 5 by a third. How many times may a third go into 5, or how many thirds of a cake are in 5 cakes? 5 divided by 1/3. When working with fractions and whole numbers, the whole numbers are written as fractions with 1 as the denominator. So when working with fractions, the whole number is also written as a fraction, and the denominator is 1. So we have 5 over 1 to be divided by 1 over 3. When dividing a fraction, we invert and multiply, or we reciprocate the fraction and multiply. That we have done. So we have reciprocated the fraction that we are dividing by, and when we multiply, what will be the result? When multiplying fractions, we first see if there is any common factor that we may use to reduce the fractions, meaning if there is any number that we can cancel. The denominators are equal to 1. The fractions cannot be reduced. So our denominators are equal to 1, we cannot reduce. The answer will be the result of dividing the product of the numerator by the product of the denominators. So we will multiply the numerators. What we get, we divide that by what we get when we multiply the denominators. So multiply the numerators, what do we get?
15.
Multiply the denominators, what do we get?
1.
Okay. So 3 5s, 15. Then we multiply the denominators. 1 1 will be 1. So we will divide 15 by 1. 15 divided by 1, what do we get? Any number divided by 1 is that same number. Any number divided by 1 is equal to that same number. 15 divided by 1 is equal to 15. The correct answer is option A. 5 cakes were cut into thirds. We could have taken a look at our diagram and make a calculation. Each cake has 3 thirds. How many times do we have 3 thirds?
5.
Right. So we have that 5 times. So we have 3 thirds in each one. But how many times do we have that, Jerry?
5 times.
We have that 5 times. That's all. We have 3 thirds in each cake, and we have 5 cakes. We have that occurring 5 times. So how many times do we have 3 thirds? There are 5 cakes. We therefore have 3 thirds 5 times. The 3 thirds occur 5 times. We therefore times the 3 by 5. And that is what teachers say to give students always. That's a very good thing, I think, though, that when teachers see a particular number occurring a particular number of times, then the teacher says that we have 7 2 times. So times the 7 by 2. Right. That's a very good idea. And we have 3 thirds occurring 5 times. So times the 3 by 5. And 3 5s, 15. The correct answer is option
A.
That's it. Which shows 14 and 5/10 as a decimal. Which shows 14 and 5/10 as a decimal.
Option B. Option C.
Right. So option C is correct. Make use of place values as in number 18. The whole number is to the left of the decimal point, while the fraction is to the right of the decimal point. So we have our decimal point right there. To the left we have the whole numbers, and to the right we have the fractional part. 14. 14 means 1 10 and 4 ones. it is the whole number part and precedes the decimal point. So put in 14. We have there what? We have 110 and 4 ones. So there we have our 14 to the left of the decimal point. 5 tenths. 5 tenths. 5 tenths. Notice the TH ending is the first digit that succeeds the decimal point. So the first digit after the decimal point is our tenths digit. So we have 5 tenths. Include a trailing zero after the decimal fraction in order to be in harmony with the formats in the option. So we have 2 places of decimal and we have 1 right there. If we include a trailing zero, it will not affect the value of the number that we have there. A trailing zero to the right of a decimal fraction does not affect. A trailing zero to the right, not just to the right, but to the right of a decimal fraction does not affect the value of the fraction. So option C is therefore the correct option. Number 22. When you count in hundredths, which number comes next after 3? When counting in hundredths, which number comes next after 3? So we have hundredths, tenths, ones. We have our place values there. And what will we do? When counting in hundredths, the digit in the hundredths position will increase by 1 each time. When it reaches 10, the 10th digit will increase by 1 and the hundredths digit will start again from 0. And later on, we will take a look at the reason for this. But what we are saying is that the hundredths digit will increase by 1 each time. And when it gets to 10, the 10th digit will increase by 1. And the hundredths digit will return to 0. And we will have that happening a few times. Like that. Is that right, Jerry?
Yes.
Okay, good. This is because the digit to the left is always 10 times the current place value. In this particular case, the 10th digit is 10 times the hundredths digit. There is the number in the statement of the problem. Increase the hundredths digit by 1. Notice that when we are counting in hundredths, it is the hundredths digit that increase by 1 each time. When it gets to 10, the 10th digit increases by 1. And the hundredth digits will return to 0. And this is because the digit to the left is always 10 times the current place value. In this particular case, the 10th digit is 10 times the hundredths digit. What we will need to do is take our number that we have there, which is 3, and we will see which number comes next after 3 by increasing 3 by 1/100th. That means when we are at 3, which is what we have there, we need to increase that by 1/100th. Therefore, 1 will be added to the 100th digit. Or we may say that the 100th digit will go up by 1. So the number that we have in the statement of the problem is 3. And we will increase the 100th digit by 1. Like that. The correct answer is therefore option
A.
There are more than one way to do it. With the understanding that when counting in hundredths, the digit in the hundredths position will increase by 1 each time, we may just add 1 to the 100th digit in 3. That's what we may do. Add 1 to the 100th digit in 3. So we have 3 right there, and we may just add 1 to the 100th digit. So add 1 to the 100th digit, and what do we get? 1 right there, and what will go to the left?
0.
Right, so we'll have 0 there, and the rest of it. With nothing to be added to the other digits, they will return as they are. The decimal point will also be vertically aligned with the one in the original number. But for the format of mathematics, that is not a very good way to approach the problem. The correct answer is therefore option A. This is really a crude way to add 1 to the 100th digit and may only be suitable for rough work. On the next slide, we will take a look at the appropriate way to do it. Because when we are adding, we cannot just take 1 and just put it right there. That's not very good for our mathematics. Although, as a rough work that you can do very quickly and arrive at your answer, knowing that you need to add 1 to the 100th digit, that may be done. But not for something that you will hand it to some teacher or something that you need to use to demonstrate how things are correctly done. So we will do it, and on this occasion we will do it the correct way. The one that will be added to the 100th digit should be shown to be 1/100th. So if we are adding a 1 to the 100th digit, it must be shown to be 1/100th. Let us look at the previous slide. On the previous slide, notice that this one that we have there is just a 1 from outer space, just added right there. But we need to show that it is actually the 100th digit that we are adding 1 to. And if we are adding 1 to the 100th digit, then the one that we are adding to it must be 100th also. So the decimal point with the other place holding zeros must therefore be included. So those must also be included, not just the 1, but all of the relevant place values, including the whole number part, which is 0, which shows that there is no whole number. And we have our 10th there, showing that there is no 10th, but we have 1/100th. And Jerry, this is your addition where you're just adding to 0. Right, so adding your 0 is very easy. So what is the result that we have there, Jerry?
1 plus 0, 1.
What else?
0 plus 0, 0. And put in the decimal point.
Right. Jerry is always paying very keen attention to detail, and he's saying that the decimal point also needs to be included. So vertically align the decimal point with the others. And then we say 3 plus 0, and that will give us
3.
Right. Great. The correct answer is option A. When counting in hundredths and we get to 10, 1 is added to the tenth digit and the hundredth digit returns to 0. On the next slide, we will take a look at why this is so. So let us count in hundredths as usual. This is done by counting by continually adding 1 to the hundredth digit. So we are going up, counting by hundredths, meaning that we are continually adding 1 to the hundredth digit. There we have it. Now, the question that we are answering is, why do we, when counting in hundredths and we have 10 hundredths, why do we return the hundredth digit to 0 and add 1 to the 10th digit? If we are going up by hundredths, that means we need to add 1 to the hundredth digit. Let us continue to count. We need to add 1 to the hundredth digit. If we are counting and we are continually counting or counting by hundredths, we need to continue our counting by adding 1 to the hundredth digit. On this occasion, we will do regular addition rather than just flipping digits. So instead of just flip the digit and move on, we will do the actual addition of 1 to that hundredth digit. When we add that, what will happen? Right, 9 plus 1 is 10. What do we do?
Put down the 0 and carry the 1.
So Jerry say, put 0 down and carry 1 to the 10th column. Alright. So that is why the hundredth digit will return to 0, and then 1 will be added to the 10th digit, as we have right there. Ensure that the decimal point is vertically aligned with the others. And also, no whole number part. This is why when we are at 9 hundredths, we get to 10 hundredths by increasing the 10th digit by 1 and returning the hundredth digit to 0. It is the same as saying that 10 hundredths make 1/10. Mistress Brown has 50,000 oranges in boxes. Which of these shows Mistress Brown's load of oranges? And notice that what we have here is not 50,000 oranges, but only a few oranges. What we are doing is making use of a few oranges in explaining or arriving at a means by which we may make the calculation that includes or involves many oranges. So we will use our small model and extend it to the larger model by using the same principle. So, if Mistress Brown has 50,000 oranges, which of these shows Mistress Brown load of oranges? But we only have a few oranges, and we will make use of a smaller model. If we have 3 boxes, each containing 4 oranges, how many oranges do we have in all, Jerry?
8.
We have 3, right? It's not 2, but 3. So Jerry says that we have how many oranges?
12.
Right. So what we do is we will take the oranges, put them right there, take a second box and put the oranges off those boxes there also. Then we will take another box and put the oranges down.
It's option B, answer.
And Jerry is saying that the answer is option B. Jerry is trying to hurry me through this because Jerry wants his lunch. No, Jerry, we will have to solve the problems and we need to explain every single one. And Jerry probably wants to eat some of those oranges. But don't eat too many of them. So we have 3 boxes, each containing 4 oranges. How many oranges do we have in all? So we may count the number of
12 oranges.
Right. So we'll count the number of oranges. And how many oranges do we have?
12.
Which arithmetic operation involving 3 and 4 did we use to get the answer?
Multiplication.
Right, so we have 3 plus 4 and that is equal to 7. And we have 3 times 4 and that is equal to
12.
Right, so Jerry is saying that it is multiplication that we should use. Therefore, if we are taking the same approach to what we have here, 50 boxes of 100, 50 boxes of 1000, 100 boxes of 50, and so on, it means that we should multiply in order that we may get the total. And that we have done by using a small model, and we put the total number of oranges down, and we realize that if we have 4 in each box and we have 3 boxes, then 3 4 is 12. Multiplication is what we should use. Multiplying will give us our correct answer. The result of 3 boxes of 4 oranges was obtained by multiplication. Those in the options should multiply to give 50,000. They should multiply to give 50,000. And Jerry is saying that the answer is option B. Well, let us take a look at option A first. What do we notice? 50 times 100. What we will use option A to do is to demonstrate how we will multiply numbers that have quite a few trailing zeros. There is a simple way to multiply numbers that have trailing zeros. Here's a simple way of doing that. First, multiply the significant digits. They are the leftmost non-zero digits. So we multiply the significant digits. They are the leftmost non-zero digits. And what are they? What are the leftmost non-zero digits?
5 and 1.
5 and 1, Jerry, is correct. So multiply those. 5 times 1,
5.
that is equal to 5. How many zeros will we have in our answer, Jerry?
2. 3.
Right, so Jerry is saying that we should have 3 zeros in our answer. So let us do that. The answer will have the same number of trailing zeros as in the numbers that we multiplied. So when multiplying numbers, we multiply first the significant digits. That gives us 5. Then the answer will have the same number of trailing zeros as the numbers that we multiply. And that is how many trailing zeros do we have?
3.
Right, so 1, 2, 3. We have 3 trailing zeros in the numbers that we are multiplying. We will therefore have 3 trailing zeros in the answer. Not only that, we were instructed by our old mathematics teachers, or good old mathematics teachers, that when we see off, it usually means that we should multiply. So we have those offs, which is the off that we have in each case is a great indication that we are required to multiply. In all cases, the significant digits will multiply to give 5. Right, so in every single one of these options that we have there, we have 5 ones, 5 ones, 1 5. Right, so in all cases, they will multiply to give 5. But what do we want for our answer? 50,000. 50,000 contains how many trailing zeros?
4.
Right. So in which option will the total number of trailing zeros be the same as in 50,000? Which one of those options will have the same number of trailing zeros as in 50,000? There are 4 trailing zeros in 50,000. In which option is the total number of trailing zeros equal to 4? We have there 50 bags of 1,000. So how many trailing zeros do we have there?
4.
We have 1 here and the other 3 there. So we have 1, 2, 3, 4. So the option that will give the same number of trailing zeros is 50 bags of 1,000. And that is not far-fetched, Jerry, because if we have 50,000 here, it is the same as 50 times 1,000. 50,000. Right. So the correct answer is option B, as Jerry stated before. Apart from the off that is present that gives an indication that we should multiply, if we have a certain number of objects that occur a certain number of times, then the total number of objects may be determined by multiplication. The word times is also used for multiplication. So we have many ways that we could tell that we need to multiply. One, if we use a small model with less oranges, the total will be achieved by multiplication. The off that we have there tells us that we should multiply also, and if we have a certain number of objects occurring a certain number of times, it means that we also need to multiply. Which of these represents array? Which one represents array? Right, so D represents the array. Each of the diagrams on the left is related to a straight line. In the diagram of a straight line, there are arrows at the ends that go in directions away from each other. So that's the diagram of a straight line. It contains arrows going away from each other, like that. Straight line contains arrows at each end that are in directions going away from each other. Those arrows indicate that a line has no end. It continues indefinitely in both directions. Others may say that a line continues to infinity in both directions. Option B is a diagram of a straight line. A line segment is a segment or section of a line. A line segment has a definite or fixed length. It therefore means that the length of a line segment may be measured, while the length of a line cannot be measured. A line segment is a portion that is segmented, cut off, or removed from a line. The most notable features of a line segment are its two endpoints. The segment is that region between those 2 points. The points are very important because they show where the segment ends. So we cut off the segment and we include those endpoints. Cut off the segment, include the 2 endpoints, and that is what we have as a line segment. So which one of those is a line segment, Jerry?
C.
Option C is a line segment. Option C is the one which represents a line segment. Which one of these represents array? Option A represents array. Array is like a beam of light when you turn on a flashlight. It is emanated, or it emanates, or it emerges from a single point. The direction of the ray is always away from that fixed point. So the ray goes away. The direction of the ray is always away from that fixed point. The diagram of a ray contains a single point and a single arrow. The point shows the beginning of the ray, and the arrow shows the direction in which the ray is traveling. The ray continues indefinitely, or some may say to infinity, in the direction of the arrow. A ray, therefore, does not have a fixed length. Its length cannot be measured. The length of a ray cannot be measured. Option A is the one which represents our correct answer. There we have a line segment, and we are saying that a straight line is a collection of points. Therefore, it is not always necessary to show the endpoints of a line segment. A line segment always ends at 2 points, whether or not we indicate them with large dots. So a line is a collection of points. If we do not show those enlarged points at the end of the line segment, it is still a line segment because it must have endpoints, because a line is a collection of points. So drop out those enlarged endpoints and we still have a line segment. What about the ray? A straight line is a collection of points, as we said before. Therefore, it is not always necessary to show the beginning point of a ray. A ray always begins at a point, whether or not we indicate it with a large dot. There is your ray. However, rays and straight lines must have their accompanying arrows to show the directions of travel. The arrows must be there to show that the line continues in both directions and a ray continues in a single direction. So although the enlarged points are not necessary, it is very important that we have in our line and in our ray the accompanying arrow, because the accompanying arrow will show that the line continues indefinitely in both directions while the ray continues indefinitely in only one direction. Additionally, it shows the single direction in which the ray is going.